Welcome, everybody. Today we're going to be talking in this video about chemical equations and the law of conservation of mass. Before we start anything, anytime you see the word law in science, you should stop and say that is going to be important because laws are very important. By the end of this lesson, you should be able to model a chemical reaction using a chemical equation and identify if a chemical equation is balanced or unbalanced. Some things to remember as we get into our lesson today. A chemical change, we also know this as a chemical reaction, occurs when some substances change chemically to other substances. In other words, the molecules and atoms in one substance change or rearrange themselves in a way that they are totally different in the new substance. We know a chemical reaction has occurred because we can observe some important evidence. Some things like color change or an odor or gas formation, bubbles, precipitates, so solids, and then light. Those are ways that we know a chemical change has occurred. In our new lesson, we're going to learn a little bit about what the things that can help us answer these questions. When bread rises, does its mass grow? Do the atoms of a candle disappear as it burns? How can we represent a chemical reaction? Some new words we're going to see: scientific models, chemical equation, reactant, product, and there it is again, that law of conservation of mass. Let's start here. Okay, we've been talking about atoms and molecules and compounds. These are very, very, very small things. So small, in fact, that we cannot see them even with powerful microscopes. So we have to use what are called models. In science, models are a representation or description designed to make a particular part or feature of the world easier to understand, define, quantify, visualize, or simulate by using multiple forms of data. So to put it simply, they're just a way of taking something that we cannot see, maybe because it's too big or too small, too fast or too slow, or too complex, and making it more accessible. So something that like a model that you would see often is the model of the solar system, or a diagram of the water cycle, showing how water moves through different spheres of Earth. Those are both models. Here's another model that we have seen more recently, the model of an atom. In our model, we are representing the particles with little balls. There are obviously some problems with this, especially with size, but we can see that there are electrons and neutrons and protons in this model. All right, and so since atoms are so small, molecules are so small, and since chemical reactions can happen so quickly or slowly, it's helpful for us to model those reactions. And we use something called a chemical equation. It's a type of model. So chemical equations involve two things, and that includes with this candle burning. They involve reactants and products. Reactants are substances that start a chemical reaction. For example, when the candle's burning, the reactants are the fuel. That would be the candle wick and the wax, and the oxygen in the air around it. So in other words, those are the things that go in. What comes out are the products. Those are the substances that are produced in the reaction. So in the candle burning example, the products are carbon dioxide gas and water vapor. And those are not things that you can see easily when you're watching a candle burn, but they exist around that burning wick. So those are the things that come out. All right, so a chemical equation includes those two things. It's a model used to show the relationship between reactants and products in a chemical reaction. In this slide, we have an example of bread rising, the chemical reaction that causes bread to rise. So you have yeast and water and flour. What specifically you have in that is glucose, is a type of sugar. The yeast eats that type of sugar, and through a chemical reaction, it creates ethanol and carbon dioxide. So the glucose is the product or the reactant, and the ethanol and carbon dioxide are the reactants. All right, so we can use this chemical equation to show that. And notice that there's an arrow in there. So the arrow, you will often hear scientists refer to that as the yield arrow. So in our example, glucose yields ethanol and carbon dioxide. All right, so glucose is the reactant, ethanol and carbon dioxide are the products. All right, so let's look at another example here. In this example, we have fuel and oxygen yielding carbon dioxide, CO2, and H2O, water. Can you identify the reactants? If you said fuel and oxygen, then you would be correct. Can you identify the products? If you said carbon dioxide and H2O or water, you'd be correct. So our second step of this, our second question, now that we know how to represent these chemical reactions, it seems that maybe when we watch things like candles burning, atoms are being lost, right? If we measure the mass before and after a candle burns, that candle's probably going to have less mass. So what's happening? Where are all the atoms going? Are they disappearing? Well, that is something that this scientist right here, his name was Antoine Lavoisier, wanted to experiment with. That was way back in the 1700s. So he carefully measured the mass of reactants and products in many different chemical reactions. What he did was he carried out these reactions inside a sealed jar. So air couldn't get in, air couldn't get out. It was a closed system, we call it. In every case, the total mass of the jar and its contents was the same after the reaction as it was before the reaction. So this showed that matter was neither created nor destroyed in the reaction, only changed. Only changed. Very, very important law came out of this. It happens every time there's a chemical reaction. If you measure it in a closed system, meaning all the matter can be trapped in one place, the air can't escape, the gases can't escape, we find that in every chemical reaction, the same mass of matter must end up in the products as started in the reactants. So in other words, matter cannot be created or destroyed, only changed. And so when we write chemical equations, we need to do what is called balancing them, right? We need to have the exact same number of atoms with the same mass going into the coming out of the equation as went in. So we call those balanced equations if they show the conservation of mass. And so how do we figure this out? If we see a chemical equation, how do we figure out whether it's balanced or not? Well, we do a couple things. We follow a couple of basic steps. First, let's identify the reactants and the products. Okay. Then we will identify the atoms that exist in those reactants and products. We should have the exact same types of atoms in the reactants as in the products. So in this case, and if you need to look at a periodic table to know what you're looking at, you can. Otherwise, you're just writing down the letter that represents the element. So in this case, we have a C, that stands for carbon. We have an H, that stands for hydrogen. We have an O, that stands for oxygen. The second step, we need to count the atoms in the reactants. So if we look at that glucose, you will see there's a small 6 just below that C. That indicates how many of those atoms are in that molecule. So we see a 6 there, so we know there are 6 carbons in that glucose molecule. I see a 12 just next to and below the hydrogen, so I know there are 12 there. And I see a 6 next to the O, so I know there are 6 oxygen. Our third step is to count the atoms in the product. If this is a balanced equation, they will be exactly the same. So let's see if they are. Well, one thing I notice right away in this kind of complicated equation is there's a 2 in front of both molecules. So there are actually 2 molecules and they both have a big 2 in front of them. What that 2 does is it is a multiple for every atom that is ahead of it in the molecule. So what I mean by that is, take that C, for example. The C has a small 2 next to it. Well, so there are 2 carbons, but then we have to multiply that by 2. So there are 4 carbons in the ethanol. But we're not done yet because there are some more carbons over in the carbon dioxide. So notice over here, we have a C. There's no number by it, so we assume there's just 1 and then a big 2. So we multiply 1 by 2. So over here we have 2 carbons, over here we have 4 carbons for a total of 6. All right, now we will add up the hydrogens. So I see over in ethanol we have a 5. We have a 5 right there. So I know there are 5 hydrogens right there, but then I'm going to multiply that by that big 2. So 10 hydrogens altogether in the ethanol, and no hydrogens here. Oh, yep, I see, I had to go double check. I see 10 hydrogens here, but I forgot there's a hydrogen at the end of this molecule that needs to be multiplied by 2. So 10 plus 2 equals 12. All right, and then finally, we're going to count the oxygens, or the O's. So I see there's 1 O here, but multiply that 1 by 2, so there are 2 oxygens. I can see there's more oxygens over here, so 2 oxygens multiplied by 2, so 4. 2 plus 4 equals 6. Is it balanced? Do those numbers equal each other? Yes, it is balanced. All right. We are going to take a look at another example here. Is this balanced? Well, we'll follow our steps. First, we will identify our atoms. We have hydrogens and oxygens. Then we will count the atoms in the reactants. I can see there are 2 hydrogens here and 2 oxygens. If I come over here, step number 3, count the atoms in the products. I can see there are 2 hydrogens and 1 oxygen. Is this balanced? No, it is not balanced because those numbers are not the same. So in high school chemistry, you would take this one step further and you would need to find a way to balance these 2 sides. For now, just you need to recognize that they are balanced or not balanced. All right, I want you to try this one on your own. Go ahead and pause the video. In your notes, you can try it. Follow the 4 steps. All right, now that you've tried it, let's go ahead and do it together and see if you got it correct. We're going to identify our atoms. We have Cl, that's chlorine, Na is sodium, and Br is bromine. We're going to count the atoms in our reactants. I see there are 2 chlorines because I see that 2 there. I see there is 1 sodium or Na, and I see 1 Br bromine. Now we will count the atoms in our products. We can start with the Cl. So I see there is 1 Cl there. There are no numbers there and no numbers in front of this molecule. So it is just 1. I see there is 1 Na or sodium. And I see there is 2 Br. So is this a balanced equation? No, it's not balanced. It does not show conservation of mass. Let's do another one. I want you to try this one on your own as well. So pause the video, try it on your own. All right, so you've tried it on your own. Let's see if you got it correct. First, we need to identify the atoms. We have Mg, we have Al, and Cl. Magnesium, aluminum, and chlorine. All right, so if we count the atoms in the reactants, we have 1 Mg. There are no numbers in front and none in the back. If we look over to our ALs, we have 1 Al, no numbers in the front, no numbers in the back. If we look over to our Cl, we do see a number in the back. It is a 3, which means there are 3 Cl. We look over to our products, starting with our top one, Mg. I see that there is no number in the front, no number in the back, so there is 1 Mg. I see the Al is all by itself, no numbers in the front or back, so it is just 1. I see the Cl has a 2 in the back, which means that there are 2 Cl. Is it a balanced equation? Does it show conservation of mass? No, it is not balanced. So in summary, chemical reactions can be represented by a model called a chemical equation. Reactants yield products. The law of conservation of mass says that what goes into a chemical reaction must come out. To correctly reflect this law, equations must be balanced. I hope this video was helpful, and I hope it helps you take your mastery check.